Thanks for inviting me, for having me here. It's my first time at IIS, so I feel honored. Okay, so today I'm going to talk about this joint work with Alex Ritter, in which we, as the title says, we kind of construct symplectic cohomology using a C-star action. And somehow the key point is, this construction is essentially new because these are manifolds which are not Liouville, not convex infinity, not the usual symplectic setup in which you construct symplectic cohomology. So that's kind of the gist of what we did. And there's a series of papers, so altogether it's 4 papers now. And I've seen on the schedule actually of IIS that Alex is going to give a talk in a couple of weeks. It's in a joint seminar. So he's probably going to talk about the 3rd and 4th papers. So today I'm going to focus on the first 2 papers in detail and nice and easy, especially assuming that some of you haven't seen this before. So I'll be polite. Okay, so in that sense, let's start with just like one single slide of reminder. What do we do in Floer theory? So kind of slightly biased, but not really. The central branch of symplectic topology is Floer theory. There, what we do is we study Hamiltonian flows. That's where the whole story about symplectic topology started. So it's finding these symplectic gradients. So something analogous to gradients in Riemannian geometry, just when you, instead of symplectic form, instead of Riemannian metric, have your symplectic form. So that's when you get your Hamiltonian vector field. And then what Floer did, he constructed this chain complex in which you capture these one-periodic orbits of this Hamiltonian flow. Those are your generators of your complex. And then in the differential, you count these pseudo-holomorphic cylinders perturbed by the Hamiltonian flow. Right, so that's a story which we all know. It's very old school now. And the upshot of early work of Floer was that indeed for closed symplectic manifolds, and that was answering Arnold's conjectures, that this homology theory, which you construct using your Hamiltonian flow, recovers the ordinary cohomology, which is a great thing. Now, for today's talk, this is not what we want. So today's talk is we think about the open symplectic manifolds in which you, using different Hamiltonians, you might get actually different cohomologies, different graded spaces, if you like. And the question is what they are. Then some old work of, well, I guess Hofer, Zender, Salomon, and other people, they still say, okay, well, in open setup, when you have small Hamiltonian, then you still recover the ordinary cohomology. So again, you know what's your Floer cohomology. But for small Hamiltonians, and the question is, what do you do? What do you do when your Hamiltonian is big? And then you get in the issue of non-compactness of your space. So that's when, talking about symplectic cohomology today, it's like, okay, well, do we have a good symplectically good understanding of the infinity of our space in order to have well-defined Floer cohomologies, right? That's kind of the main technical issue. Now, the way it is done traditionally. Again, going back to, yes, Floer, Hoffeld, Vysotsky papers, and then later by Viterbo, where he said, like, okay, well, let's assume that our open symplectic manifold is Liouville, which means it has a nice infinity. So apart from some compact set, it has this cylindrical end, which the slice is your contact manifold, then times some half line, parameterized by radial coordinate. And then story is that that's good enough, meaning if you have such setup, and if you use Hamiltonians which respect the setup, so they are linear with respect to this radial coordinate, then you're still tamed, meaning your Floer cohomologies are well defined with respect to these Hamiltonians, and you can also get the continuation maps, right? So when you have HF from one of these Hamiltonians and go to HF to the other, whenever the slope of first one is smaller than slope of the other. So kind of going from the smaller to bigger Hamiltonian. That's doable. And that is all due to the fact that there's a maximum principle here, which works for these pseudo-holomorphic curves, and also for those which gives you continuation map. And that only works when you're going from smaller slope to bigger. So you get a directed system of graded groups here. and there's a limit to that. This is what we call symplectic cohomology. Again, this is kind of repeating some old story, which I'm sure most of you know, if not all. So that's kind of background, but and then I just want to give you an example, also traditionally known. So this is Viterbo isomorphism, saying that this symplectic cohomology ring for the cotangent bundle, or the kind of canonical open symplectic manifold, recovers the very nice, so it's homology of the loop space together with a string product, something somehow coming from algebraic topology. So this new invariant you get from the open symplectic manifold, it's very interesting, and it can give you some interesting rings. So not only see for the closed symplectic manifolds, the story finishes with ordinary homology. So for open, the question is, okay, what we can get for a given open symplectic manifold. So then we get to C to the n. And what is C to the n? Somehow I would put some diagrams. So we have Liouville manifolds, and there's C to the n being here, being Liouville, and there are these our manifolds which with the cis direction. So the story from previous slide is about Liouville manifolds, where you can define the symplectic cohomology. In particular, that works for C to the n. But work of Alex and myself is about these open symplectic manifolds with the cis direction, which of course includes C to the n. C to the n is everything. So that's somehow I want to go from this story to actually this story, but kind of going back to C to the n because it's a very easy example to understand. So, and moreover, this Liouville structure here and this cis direction there, they're giving you the same structure geometrically, which we're going to see. So, okay, which cis direction is natural for C to the n? Well, just a simpler, just a scalar weight one action, right? And that action has a moment map. So moment map is simply saying that the S1 part of the action is symplectic. It preserves the symplectic form, and it's also Hamiltonian, with the Hamiltonian being the distance from the origin, right? So somehow everything gets together for C to the n because C to the n is so nice. Now I put like 3 observations here, which we can take from C to the n, and I want to get from that to any this symplectic manifold with cis direction. Okay. So the first observation is that well, it is Liouville, and the radial coordinate. The radial Liouville coordinate is actually the same as moment map. This you can, it's like a easy exercise. Then as a consequence of the previous slide, well, being Liouville, then you have well-defined Floer cohomologies with respect to this radial coordinate and the continuation maps. So together you can define symplectic cohomology for C to the n with respect to this Liouville structure, which by the way is same as the moment map structure. So the radial coordinate is same as the S1 moment. Okay. That's kind of easy considering the previous slide. And the second observation says, okay, well, we have this well-defined, but what is it? What is symplectic cohomology of C to the n? Well, then you get in the story about the grading, which really solves the problem. So the general situation about in symplectic world is that if your Calabi-Yau, if your Chern class is 0, and furthermore, the first cohomology is 0, being Calabi-Yau is the canonical bundle is trivial. Having the first cohomology 0, meaning all the trivializations are the same, which means that there's a canonical Z grading on all Floer cohomologies here. In particular, so you can grade these Floer cohomologies, which gives you the symplectic cohomology. And then what you do here to get to 0, which is the upshot of observation 2, is to say, okay, well, let's use Hamiltonians, which are very nice. So just lambda h. Not lambda h infinity, but exactly like these clean Hamiltonians, I like to call them. So why they're good? Because, and putting lambda to be some irrational slope, because h is rotating. H is like S1 rotation. So you take a rational slope, it means you rotate for some time and you don't stop. You don't stop in a full rotation, which means, you know, what are the generators of this complex? Well, basically S1 periods, but then, well, with a, you know, like lambda rotated S1 periods, but the only one which happens there is the origin, the irrational slope. So the outcome is that this Floer chain complex has just 0 being a generator, and then the grading you can compute by formulas, but basically the grading, this Alexander index is like how much your canonical bundle gets rotated using this Hamiltonian. And then the lambda comes as a multiplication. So if it was just H, it means how much canonical bundle gets rotated with the S1 action. That's this 2n. And then lambda gets like multiplied here. So anyway, the outcome is that you always, you get explicitly what this Floer cohomology is, and the grading, like in these direct limits, it needs to, these continuation maps, they follow the grading. And then if you go from grading 0, which is for lambda very small, to grading minus 2n, you cannot save your cohomology group, it has to die. So eventually it's zero. It's zero in the direct limit in particular. But already it's 0 when lambda is 1. So anyway, so the point of observation 2 is that this symplectic cohomology, which is well defined for c to the n, is 0. And that's what we're going to take further in considering this family of spaces. Okay, the third observation, so last but not the least, is that we can also consider these more interesting Hamiltonians. So something of type c to the h, which slowly increases the slope and eventually finishing as lambda h. Okay, I like to call them, well, they are convex, right? So we start with a small slope and then increasing slope up to lambda h. What's happening here is that unlike our lambda h from the previous observation, which had only origin being the periodic orbit, here you do have the origin, but you also get when you get period 1, you get all the S1 orbits, and when you get period 2, you get them, but like doubled, and then when you get period 3, you get them tripled, and so on, all the way up to the floor of lambda. So you actually get a lot of interesting orbits happening, and they're all, for the example of c to the n, they're all going to appear in families. With c to the n, your hypersurface is sphere S2n minus 1, so they're all going to rotate by the S1 action. So you're going to get families S2n minus 1, S2n minus 1, and so on, kind of lambda times. When it finishes, and this lambda is a rational slope, so there's no more orbits. So this is happening when the slope is integer. Okay, and then furthermore, so this complex is very interesting, but furthermore, it is filtered by the action functional, which is exactly when you calculate, it's going to be this y coordinates where intersect your y-axis. So it means, so as you're going further, your filtration is decreasing. So somehow what I want to say, it follows the value of h. As you're going further, that's exactly giving you filtration of your chain complex. Now the story from homological algebra says you have a grading on your Floer complex by the Alexander index. You have filtration, so that gives you spectral sequence, which converges to your cohomology. Right. Now, a priori, the spectral sequence should converge to the homology of CF, so Floer cohomology for lambda. But then you can construct these nice convex Hamiltonians, so they're like, so that the chain complexes are inclusion of each other, so you can kind of go further and further. And in the direct limit, you can get spectral sequence which converges to the symplectic cohomology in that limit. Okay, and then what are going to be the columns? So what's going to be the E1 page of the spectral sequence? Well, that's going to be the local Floer cohomologies for these. So what we see in this board, so you get the sphere family of orbits, and then you do local Floer cohomology. There is going to recover you the ordinary cohomology of your sphere. And then in the next pages, the differentials are some differentials, Floer differentials between these guys. So that's what we chase with the later pages in the spectral sequence. Now, so that's one fact. That's this third observation. But what is good is to consider the previous observation, in which SH is 0. So you know that this spectral sequence has to converge to 0. So in other words, you know that all these classes here, they have to cancel each other somehow. Now, in a simple case, like maybe topologically simple case of C, where this is all you get, there's only one way these classes can cancel out, and that's this one. Just bear in mind that this is not the usual spec. So this is cohomological gradient, P plus Q, and this is P. This is your filtration by action function. So all the differentials, they go up by rho 1. So this is D2, D3 would be if you go from here to there and so on. So yeah, the upshot is like you definitely know who is canceling who in the spectral sequence. And that's what we can take from C to the n. Now the questions for today's talk is really to go in the direction of these symplectic manifolds with the C directions in which you try to repeat the whole story. You say, okay, I have a symplectic manifold with C direction, which is nice enough. Can I create a Floer cohomology using the S1 moment map of the action being my radial coordinate, because I don't per se have a radial coordinate. What happened in C to the n is that this is all the same thing, radial coordinates, moment map. But forget about Liouville, I just have a C direction, I have a moment map, and if I mimic that to be my radial coordinate, and by that way I define symplectic cohomology, is it well defined? Do I get this? And what about spectral sequence? Like how much this idea can go through? That's the question. And what interesting invariant I could get from that, right? Not just the story on its own, but what could be the outcome of this construction? Okay, so let's think about this generalization first. How much we can generalize this. Then we get to this first definition of what is a symplectic C-star manifold. So what you definitely have to have is a symplectic manifold with a pseudo-holomorphic, so almost complex structure, which C-star action respects, connected with just only for brevity, and then the S1 part being Hamiltonian, because this Hamiltonian is exactly going to mimic our radial coordinates. So we need this. Okay, then you ask yourself, okay, well, is this enough? You think about the proofs for C to the n, what was coining the proofs. You realize that you also need something more. You assume that C-star action is contracting. So think about C to the n. C-star action contracts everything to the origin, and in particular, origin is the only fixed point. So the fixed point set has to be compact, and all the other points are kind of moving towards them. So you always have this limit. Otherwise, if there was no this limit, what would happen is that this S1 action, S1 moment map would be improper. So like the energy surface with moment map would just have non-compact hypersurfaces, which is not, you just don't work with this. There's no way to do Floer cohomology for this. So we definitely need it. And as a side thing, what is interesting is in this setup, which appears a lot in algebraic geometry and in geometric representation theory, you can define the other limit. So all the points which have limit in both directions of C-star action, and that's what we call core. Now again, if you get back to this picture, you forget about the C-star action going to Liouville. This is exactly like C-star action is mimicking, or the R plus part is mimicking the Liouville vector field, and this core is mimicking your Liouville skeleton, right? If instead of this, we're talking about the limit of the flow of the R plus action. If this was like C to the n, but if this was Liouville setup, that's how you define your skeleton. Like all the points which have limits when you're going along the Liouville vector field in both directions, right? So that's maybe a thing to have in mind. Although the intersection between this setup and Liouville is exactly C to the n, so you can't really, this is not Liouville, but this is kind of mimicking that scenario in order to get some analysis done. Okay, so then we prove this theorem, which this is just like a geometry and topology of these spaces, kind of recovering the old results like to Atiyah-Bott, just in this more broad setup. So this core, this mimicking of skeleton is going to be compact and connected. And in nice setup where things are, let's say if Y is a variety, then this core is a deformational retract of Y. So when you think about cohomology or anything, like any topological invariants of Y are the same as topological invariants of the core. And you have this localization of the total cohomology into fixed components. So all the fixed components are inside the core. They're like, core is, you have some fixed components of the C-star action, and there are some C-star flow lines between them. And that's what core is. It's like a union of fixed points together with the flow lines. That's exactly what it is. So, but then, so the total cohomology breaks in the cohomology of these fixed components. In particular, because of this and connectedness of Y, there's a unique minimum of the H, because these are Morse-Bott indexes. So the background story is that this S1 moment map is a Morse-Bott, and the fixed components are the Morse-Bott critical locus of the Morse-Bott function. So there's a unique minimum here. Okay, so this is a setup which we get, and these are like some topological consequences which we get for this setup, which of course works for C to the n, where everything's very easy. But this can give us many more examples. Now the key question is this good enough? So you assume this is direction, which is very nice topologically, it's contracting, it's tamed, but is it good enough to use this moment map for your Floer cohomologies? Like, do you have some certain maximum principle, or do you get monotonicity lemma? Those are like two different ways to tame your, to make your Floer cohomology well defined. And the answer is, well, a priori, not. So we tried use this conditions to get some maximum principle, but really, any way you try it, you just hit a rock, and then we just gave up in that attempt. You can think about proving monotonicity lemma. So in the way, and somehow connecting to the work of Joel Groman, who essentially, so he says, okay, my open symplectic manifold, that's another work on extending symplectic cohomology for non-trivial manifolds, which says, well, assume that I have some good metric, which is called geometrically bounded, metric which is compatible with symmetric form, and then let's use some Hamiltonians which are dissipative, which means they spend energy fairly, and then if that setup works, then you have well-defined symplectic cohomology. But the problem is, a priori for this setup, to our knowledge, it's really hard to prove any of this. Like that this metric, which is coming from here, it's bounded in this sense, and these Hamiltonians you get from the S1 action are dissipative. It's just like, all these definitions are abstract, so it's really hard to get that done. So what actually happened in the between, yeah, that's the issue, as I said, maximum principle doesn't really work. So what happened actually while we were thinking about how to make this work is that we got additional condition, which was already given for our examples. So I mentioned this story about C to the n as a motivation, like because C to the n is very simple. But our examples were really some things called symplectic resolutions, like Nakajima-Kuyu varieties or hypertoric varieties, manifolds coming from geometric representation theory. Now they, being resolutions, they are projective resolutions, so they have some proper map to C to the n actually, and that's where we found the key condition which we need, which is you have to be proper. Well, you don't have, but if you are, then everything's fine. So if you're proper above something which is convex end, right? This was the end of the Liouville manifold. So you have a map to this, and then here you're good because for the end of Liouville manifold, the analysis works, the maximum principle works. Then you're good. Now, of course, everything has to be compatible. So our almost complex structure has to go to the convex structure, and then the Hamiltonian vector field needs to go to something times rep, because all this data on the convex end is giving you maximum principle there. And because you're proper, then whatever is here in compact is going to be compact upstairs. So all is good. And then again, yeah, so this is what we discovered that really holds for these symplectic resolutions for which we wanted to get this story done, because these are like equivariant resolutions of affine singularities. Then you put it in C to the n, everything is equivariant, so it satisfies this condition, and that was the magic. That was the magic, and then those manifolds in the end we called symplectic C-star manifolds over a convex base, because this is a convex base and they're over it, and then this setup indeed works. Then apart from these symplectic resolutions, they don't have to be resolutions really. What you need, considering this condition of properness, you really want to be algebraically, so projective morphism over a fine variety which has a contracting C-star action. So these are, let's say, algebraic geometric, and there's plenty of these examples in nature, where whenever you have it, how do you get from here to there? Well, okay, so you have a fine variety, you can embed it in C to the n. If it has a linear C-star action, you can equivariantly embed to C to the n, and then you compose with P to get this story. Because eventually this is going to have a linear action C to the n, which you can again send to another C to the n with the same weights, if you like, to make this like a multiple of reb. Because in reb, S1 action is reb, so in C to the n. So okay, so this is kind of the upshot. Okay, we get a lot of examples from algebraic geometry here. So yes.
Those examples, it's obviously not doable, or what's...
Right, yeah. So not obviously, but I will go back to this story. Let's forget about that. When you have this C star fixed locus, whenever these are not just points, you're going to have symplectic submanifold. So because of the Stokes theorem, then you cannot have exact form. So not globally exact. So that tells you, like, whenever you're in this symplectic C star manifold story, unless these are just points, even when they're points, then this flow is going to give you like some P1 maybe, which is also like symplectic submanifold. So that would not abide the Stokes theorem. So we see, like in C to the n, what happens is you just have one point which is fixed, and everything contracts. So there's no space to getting like submanifolds, because these are like holomorphic submanifolds, so they're going to be symplectic. That's why it cannot be Liouville. Liouville at infinity, that's a good question. Like not necessarily Liouville, but somehow to have the convex end. Whenever it's a resolution, at least, that's not going to work unless it's a resolution of isolated singularity, because the picture is like when something is a resolution of non-isolated singularity, then all these singular points, they're going to give you some holomorphic fibers here, in which you can get some maybe P1s or something, which go all the way to infinity. Which again, by Stokes theorem, it messes up if the symplectic form was exact infinity. So amongst these symplectic resolutions, the only convex examples are AD resolutions. So they are indeed convex, but that's it. That's only them. I'm going to mention some of them. And for them, Alex already had a paper in his PhD of this like symplectic cohomology story. So yeah, but that's a good question. This point, I keep saying that this is strictly not Liouville, but this is sort of the argument that they get, and why we're kind of going into the unknown territory from the symplectic cohomology perspective. Okay, so yeah, you get a lot of spaces from like geometric representation theory, and but also algebraic geometry and the toric varieties, which are in symplectic topology are interesting examples. So most of them not being convex. So exactly new spaces for us. Okay, so then let me just basically repeat what was the consequence of the previous slide, which is when you have the setup, so your symplectic system manifold over a convex space, then your Hamiltonian Floer cohomologies are well defined because of this projection trick. And you can define your symplectic cohomology. It's going to be unital ring. You can get pair of pens as well. And moreover, so now this part is interesting. Because a priori, we use Hamiltonians which respect the C star action. They come from the moment map of the S1 action. So a priori, we should put y and phi. So it's a invariant of a manifold together with the action, which gives you all the data. Then you ask yourself whether this action really matters. And in the end, it doesn't matter when you're in this setup. I mentioned from previous slide, when it's like a morphism over a fine, and when these actions commute. So when they're coming, for example, as a C star subgroups of a big torus. And essentially that it's, it was a great, somehow, we were happy when we got this, but when you think about it, what's going on is like, all these, they project to X, which is in C to the n, and the moment map here for the S1 action is just like it's a positive weighted sum of the coordinates squared in C to the n. So then, one SH, the other SH, they shouldn't, it's like, you get sum of ni zi square, sum of mi zi square. So when you put enough big lambda, this can majorize this one and vice versa. So you can make like a interpolation of continuation maps to kind of go from one to the other. So this is not that much of a surprise. And indeed, what you're going to see in Alex's talk, I guess, in 2 weeks, is that for toric varieties, for these same projected toric varieties, this symplectic cohomology ring is going to recover the Jacobian of the superpotential. For people who know toric varieties, you get one with polytope, out of that you get your superpotential, then you get this Jacobian ring by using the derivatives of this, and that ring is actually going to be isomorphic to the symplectic cohomology constructed in this way, which is interesting. So you get something which makes sense. It's not completely random ring. And the other thing is, going back to this motivation for C to the n, remember observation 2 was that SH was 0, right? And the proof for SH being 0 for C to the n was that we had this grading, so coming from a Calabi-Yau condition. Now the same story works, it just the proof gets slightly more complicated. So the story is that unlike in C to the n, right, in C to the n, your core, your fixed locus is just one point, very simple. Here you get a couple of these components, but the upshot is that the Floer cohomology for these clean Hamiltonians, so when you fix exactly lambda h with a rational slope, again, all the orbits are just going to be fixed orbits here, and then you just need to keep track on Conley-Zender indices. Like in C to the n, you kept track, this was like 2n lambda. Here what's going to happen is something like that, plus some topological information on the fixed locus together with the weights, but that information is finite. So finite plus lambda times something positive, that goes to minus infinity as you put lambda goes to infinity. So indeed the same kind of trick, which is like you start with your cohomology and then it's going to drop eventually. So eventually the direct limit is 0. So that works. But you need to have the grading, which means you need to be Calabi-Yau. And indeed, right, for these toric varieties, when you're just Fano, your ring is going to be something non-zero. So, right, now we get to the culmination of today's talk, which is some actual application of this, not a story on its own. Like, yes, we can construct symplectic cohomology using this method, but actually you can get some interesting new invariant using this symplectic cohomology and using a certain cis direction. Which is this filtration. So how do you get filtration? Well, just go back and think like, wait, how do we construct symplectic cohomology? Well, we start with a small Hamiltonian with a small slope, and you get to the Hamiltonian with certain slope, and then you go further and you go further. Then you ask yourself, okay, well, these continuation maps, if I know the kernel, so the question is, when is any class here, which by PSS gets to quantum cohomology, when this class gets vanished in this direct limit, and if it gets vanished, of course. Now we've seen if in the Calabi-Yau story everything gets vanished. So in that story, every class here needs to disappear for some lambda. But let's just keep track on that. So keep track on the kernel of this map, and this intersection is just to kind of get infimum. So when is the first time that the class gets killed in this like direct limit? That's the definition of filtration. And it's not, I guess it's one of these spectral invariants people talked about since long ago. So, when some class dies and reappears and so on. So, but if we fix this thing, then you get, right, what you get is interesting algebraic object. It's a filtration on your quantum cohomology by ideals of the quantum with respect to the quantum product. Why they're ideals? Because, this belongs, you can make a diagram with a lambda plus delta, and then this diagram commutes with the pair plus product and so on. So eventually you get some compatibility. And then of course, if SH is 0, it means that any class here eventually has to disappear. So this filtration exhausts QH. Otherwise you can just define, the filtration at infinity is QH. Okay, so that's maybe the main invariant of our work. Like the upshot is you start with your symplectic manifold with the cis direction. Floor theory makes sense because we put these conditions, and as a consequence, you get some filtration of the quantum cohomology ring by ideals. And this filtration actually depends on the action. So using different actions in practice, we've seen that we get different filtrations. Although the symplectic cohomology itself, in most examples, it doesn't change; it's somehow constant, but these Hamiltonians are different. So I guess the continuation maps, they remember which action was in charge. And of course, because this is all compatible with grading, you also get filtrations on each graded piece, which is interesting. Okay, so that's like a side application which come as a side product of just us wanting to understand, can we define the Symplectic cohomology? Now, of course, if quantum cohomology is just too difficult to handle, you can specialize these ideals. These ideals, they have some bases, and then this basis has some coefficients in Novikov ring. You can just put all the Novikov part to be 0, and you get a filtration on the ordinary cohomology by kappa ideals with the same ranks. So somehow linear algebra, from the linear algebra perspective, it's the same information, but you can get some filtered ideals on the kappa product, which might be interesting to compare to other filtrations in outside of symplectic topology. Okay, now for the rest of the talk, I'm going to talk about this filtration, how much we know about it, how much we can compute it, because again, this is floor theory, so you don't expect to be able to compute everything. You can talk about things, define things, but computability is always the hard one. And I will try to convince you that at least for these Hamiltonians, which are coming from sister actions, you can use the knowledge of sister action to kind of actually get some information on this filtration. So maybe the first thing to say is that you can always at least say explicitly what is the filtration at integer times. So when you kind of go from quantum cohomology to the slope of integer. So like basically when I say integer times, I mean h1 would be rotating once, right? Rotating once S1 action. hn is rotating n times, and I put n plus because you want to hit the irrational slope. Otherwise, everything's hf for hn doesn't make sense. Everything's a periodic orbit. Okay, then the question is what's that filtered piece? Well, actually, Alex in his previous work, he proved that these in the setup of convex Liouville or just convex manifolds, this continuation maps using this S1 rotation is recovering just the quantum product with the Seidel element. So there's some general story when you have S1 action, and that S1 action is Hamiltonian, you can associate to its Seidel representation together with the Seidel element, which is the element of quantum cohomology. And this mu is Maslow index of the S1 action. Now, what I'm saying here is that these continuation maps, you can recover them using the Seidel element, which then in particular says, okay, well, at least the integer levels of filtration, I always know that it's a kernel of multiplying by quantum product with Seidel element, which in particular says, okay, if you know something about the Seidel element, then you might know something about this. And because of this as well, you also have the connection with so quantum cohomology and Symplectic cohomology, defined this way, are related, that SH is either this, or in other words, it's a localization of QH with the Seidel element. So it's a kernel of when you multiply it enough times. So that's the relation between SH and QH, and actually in our last paper, which Alex is probably going to talk about, we compute both of these for toric varieties. So you get here this being localization of this with respect to the toric divisors. Okay, so at least we know the integer layers of this filtration, and then there's like some side proposition which we proved, which is to say, okay, well, I know what this Seidel element is, at least in some certain nice topological setup. So it's going to be, and it goes back to some previous work of. So this formula was, I guess, already known for compact symplectic manifolds by other people, and then Alex proved this for the open case of convex symplectic manifolds, and we just here said, okay, well, all the analysis works, so this formula still holds. So you kind of know this Seidel element being a Lefschetz dual class of the minimal locus, the minimal fixed locus of the sister action, plus some higher Novikov part, which when you're Calabi-Yau, you don't really know. When you're not Calabi-Yau, you can know this cleanly, like when it's fun. So in particular, it's not zero, so then at least you know that first, so F1 is not the whole cohomology, which is some non-trivial information. It's again, these are Floor invariants, so you don't, any information is a good result. Like you expect to get everything computed, but some partial information is nice. Yes.
So what's the one? What does the one mean?
Yeah, like time one. So that's this n being one, because then n being one is just kernel of the quantum product with the z element. And I'm saying z element being non-zero means that, kernel is not the whole thing, because if the kernel is with the whole thing, then Q5 would be just zero, right? It's like multiplication with a non-zero element. So, at least unit, right? So unit, you multiply with Q5, you get Q5. That's non-zero. So at least unit is not in the kernel, which means filtration is not the whole thing. When you, of course, because these are ideals, when unit gets in filtration, then everything's, everything is in filtration. Okay, so this already gives us like, like some simple example worked out. So A1 resolution. So stepping aside from C to the n, which was boring, A1 resolution is the simplest symplectic resolution sense of these geometric representation theory people. So you get A1 singularity here, which you can transfer with Veronese to C3. And in these coordinates, you have the most trivial action here. That action lifts to the, again, most trivial, like just a C star fiber contraction action. And then using this datum, what happens is that because this satisfies this principle, your PD of Fmin is just CP1, that's a fixed locus. PD of Fmin is going to be -2 of that, so that's going to be non-zero, which means that Fn is non-zero, but I put H upper than 2 because you can generalize this, but H2 is the first part, because z element is going to be in H2, and H2 times H2 goes to H4, there's no H4 here. So that has to vanish when you multiply by quantum. And then the F2, you already multiply z element 2 times, so you get to H4, which is 0. So that then everything is in kernel here. So here you immediately know what is your filtration for this, let's say, simple example, using this like maybe first principle which we have in hand. Now another story, like as a side thing, is that we thought about the natural, what the nature of this filtration and with what we can compare it to from the known filtrations coming from geometry. And there is some old story by Atiyah-Bott where you forget about the Floer theory, just differential geometry of the S1 action on Kähler manifolds. There you can consider this Atiyah-Bott filtration. You get basically from just considering. So first of all, there is this decomposition of total cohomology with the cohomology of the fixed components. These guys with their Morse-Bott indices, and then the filtration there you can get from the Atiyah-Bott story is consider all the fixed components from a certain, take like the maximum of the moment map, and then take the second maximum and the third, and so somehow you're going from maximum to the minimum, and you're slicing along the value of so you're just following the value of the moment map. So that's kind of very simply defined, and actually this is going to be kernel of some certain maps. So, and these maps, they respect the cup product, so you're going to get cup ideals. And this very much looks like our Floer filtration, which indeed finishes with a minimum, because minimum is going to be unit. And if you're ideal, you have unit as a whole thing. So it goes, and in examples, it goes from these, it captures first the cohomologies, which have bigger values of H, and then it goes towards the one which have smaller values of H. It's just like as a general feature. But then comparison is, well, let's see, in the A1 resolution. So in this case, Atiyah-Bott filtration will take the whole CP1 because there's only one fixed component, that's it. So 0 takes CP1. Here our filtration takes the H2 class in CP1 and then the H0 class in CP1. So kind of it filters. It can distinguish different classes within the same fixed component, which is interesting and kind of non-trivial from this perspective. Like you can kind of with Floer theory, you can kind of go through a single fixed component, which you cannot using the Atiyah-Bott story. So in the A2 resolution, which is our second most easy example, instead of A1, so you have this Z3 action acting by, third root of unity and then to the -1. So it's like SL action. The core here is going to be so here we have isolated singularity. So above it, you have the CP1 and CP1. That's your exceptional locus here. So that's the geometric background. And the action, let's take this particular action on this coordinates, so t squared t. Then what's going to happen in the resolution here in y, when you lift this action, you're going to, in the core, one CP1 is going to be fixed, and the other one is going to be the point which is opposite from the intersecting point. So the picture looks like this. So you have one CP1 fixed and one point on the other one fixed. So the Atiyah-Bott filtration, because here the moment map, so this is going to be the minimum, the moment map is going to be maximum. So we said the Atiyah-Bott filtration takes the maximum on the moment map and then goes further. So it takes this chunk and then this chunk, which is the so kind of two steps. Whereas the Floer filtration here, which is going to take indeed the maximum locus here first, this point, and then it's going to take H2 class here, and then it's going to take the H0 class as well. So it again goes through this fixed component in an interesting way, in a non-trivial way. So it kind of compares in a sense that the same motion, like you kind of go from the maximum towards minimum, but it can get more filtered layers. I guess because with Floer theory, it just things get more complicated, so you can get something refined. So it's kind of looks like a Floer theoretic analog of what Atiyah-Bott filtration does. I just wanted to kind of mention this as an interesting feature. And then in the end, we get back to remember in C to the n, we talked about spectral sequence at the end. And that's why we talked about spectral sequence. Well, because, it was an interesting story there. Like we can get some interesting Floer chain complex and that converges to SH. But really why we talk about spectral sequence is because it will give us a way to compute this filtration. So which in C to the n was simple because there was, you just have one cohomology class. But for these more general manifolds, you can get, this spectral sequences are actually giving you a good tool to actively compute it in examples. Because as we've seen before, you just get some partial results on what this filtration can be, but no general results. And that's why we get to spectral sequence and the story becomes much more feasible. So recall on C to the n, what we had was we get this Hamiltonian, which is convex, and we realized that with the action function, we can filter it, right? Because this was Liouville. Now in this story, and this is like very much the most technical part, which is to say, okay, well, we can actually do this for our story because for this convex end here where we project, so it's not necessarily Liouville, but it's convex end, and there's a modification of the action functional in the previous work of Alex and McLean, where they kind of mimic the action functional on the convex end. And we need to modify this actually to get the filtration on our chain complexes. So this is all good. And this filtration also follows, this sub-complex condition, which you need in order to get the spectral sequence to SH to go in a direct limit. So the outcome is you do get a spectral sequence, call it Morse-Bott-Floer because you get these families, and that's another technical issue. So you get these families of orbits, now you need to deal with them and to prove that the local Floer cohomology recovers the ordinary cohomology, and then this is E1 page. Now there's a lot of symbols here. Let me just briefly say what they mean. So this is just the not column. So the 0 column, which is just the ordinary cohomology, that's your Morse-Bott, or those are the orbits with 0 period, right? As we've seen in C to the n, there was just a point. And these are higher orbits, which same for C to the n, those are orbits of S1 action with higher and higher periods. So in C to the n, things are easy because the S1 action is locally, it's free outside the origin. So you get periodic 1 orbits, periodic 2 orbits by doing that twice and so on. Here, in general, the action for a general, like we'll see in this A2 resolution, the action can have these non-trivial isotropy points, so Z2 isotropy, Z3 isotropy, which will give you, the periods here, these TPs or these M's being bigger than 1. So 1/2 period orbit, 1/3 period orbit. So these columns, they will have, this is period 0 orbits, so constant, so fixed locus, and then you'll have, 1/2 fixed locus, and then maybe maybe 1/3 fixed locus, depending which isotropy is your sister action you have. So somehow knowing this E1 page is knowing the geometry of your sister action. So knowing what are the weights here in the weight decomposition here, because they're going to give you these non-trivial rational periodic orbits. And then in the end, this period becomes 1, which you get the whole hypersurface, like in C to the n, like just a hypersurface of your, so cohomology hypersurface, and then it repeats again. So after period 1, you get 1 plus 1/3 or whatever you had, and then so it just becomes periodic. Now that's the general kind of picture. We'll see examples, so it becomes less abstract, I guess. And the outcome is, which I already mentioned, why we're doing this spectral sequence, for us at least, because it recovers the filtration. So a point in a knot column is in the filtration piece lambda, if and only if you kill it with a column which has period up to lambda. So that's kind of coming from this from the construction. So if you understand your E1 page of the spectral sequence and you know your differentials, you can in principle compute this filtration, which for a lot of examples work, and that's why this is our tool of computing the filtration. So let's then go back for the last 10 minutes of the talk. Let's go back to our examples, which we already seen, but from the spectral sequence perspective. So A1 resolution, right? That was a resolution of this A1 singularity. Then we had this most trivial sister action, which lives to the natural sister action there. What's going to happen is same as C to the n, this action apart from the fixed locus is actually free. So the only these manifolds of orbits are only going to happen in the integer times. So only time 1, time 2, and so on. And that's going to be your hypersurface here, which is S3 mod Z2, which is like RP3. Okay, so the action is free, so there are no B, A, or B, so just integer columns. So indeed, you're going to have something like this. And before someone says, wait, this is not RP3, I'm just going to say, well, in computations, although we don't need for theory, but in computations, we always assume characteristic 0, so that we don't deal with like some Z2 happening here and what to do with it. So one could do it, but we didn't do it. We assumed, for the sake of these papers, like let's put characteristic equal to 0 for this and for other reasons. So this RP3 is same as S3 in terms of characteristic 0 cohomology, right? So you get S3 here, S3 there, S3 there. And then similar like C to the n, what we had that the SH is 0, and this is indeed Calabi-Yau. So you know that everything has to match up with everything. And then, because again, the grading in these spectral sequences is made so that any class needs to go up by 1. So this class has to be killed by this one. This class has to be killed by this one. And that's what gives you filtration. So you say, okay, H2 is killed by column 1, by time 1. So it's in F1. H0 here, it gets killed by column of time 2. So it's in F2. So you effectively read this filtration using the spectral sequence. As we had before, using the Seidel element, but this is just a say, okay, well, let's look at it from the spectral sequence perspective. And in the end, let's do the A2 resolution. So again, that was the resolution of A2 singularity. So again, you can bend in C3, get these coordinates. Core was the 0 fiber above the singularity, which is CP1 times CP1. And then we, in the previous example for Atiyah-Bott filtration, we use, I think, this or that action. Here I'm saying, okay, well, actually you can choose many different actions. And as I said, this filtration is actually depend on the choice of the sister action. And the fixed locus, of course, are going to depend on the choices. So this first action, so these are all actions in these coordinates here. And I'm claiming you can just pull it back. So this being crepant resolution, you can always pull back sister action. So when you pull it back and you see the action on the core, how it looks like, this is what's going to happen. So the first action is going to give you 3 fixed points. Second action is going to give you 1 fixed point, CP1. The third action is going to swap these two. Okay. So we know the fixed points, which we need for the spectral sequence anyway. But then how do you find these manifolds of orbits, right? So in the previous example, we just needed the hypersurface because the action was free outside of the fixed locus. So we don't care about these rational periods. So like periods smaller than 1. But here, what's actually going to happen is, the weight, it's all about weight decomposition. That's the only thing you have to know. Weight decomposition of this is like weight one flow. Weight one flow gets here as weight -1. It gets coupled with weight 3 flow because this is a holomorphic symplectic setup where you kind of weights, they double to sum to 2 for other reasons. But anyway, just trust me that then there's a weight 3 flow coming out here, weight 3 flow coming out there. In other ways, you can actually see it from here because in C3, there is weight 3 flow coming out from the 0, which then in the resolution gives you these 2 lines. Actually, that's another way to see it. So because there's weight 3 flow, it's fixed under the Z3 isotropy. So this S1s here in the hypersurface are going to be 1/3 periodic orbits. So that's how you see in practice, like just knowing your cis direction, you see what are your columns with the smaller periods in one. So you get one circle here, one circle there coming from these 2 Z3 fixed lines. Here what's going to happen is you have weight 1 happening here, weight 1 gets -1, this goes to 2. So here you're going to have like one complex line. These are 3 pictures, right? So just imagine there's no this. So there's complex line here, which weighs 2, which reflects this part, right? So when you're going down the resolution, there's a complex line with weight 2 in C3. So that gets lifted here. So that's how you get B1 here being this S1. And here there's not, like, that's all weight 1. The same story goes here. So altogether, just understanding the C-star geometry, you get these rational, so the columns with rational periods, and then you can get your spectral sequence. Now, of course, here you need to compute your colonies and indices, but that's, we just found the formula for this again, using the fact that this is all coming from cis direction. So, and also pseudo-holomorphic cis direction. That's the key thing. Like you can compute colonies and indices explicitly. So you get where to put these 2 S1s from the previous slide, right? You have 2 S1s here. They again repeat, of course, because you just double them. And then you get your time 1, the whole hypersurface. And then, as I said, it repeats. So basically for the spectral sequence, you need to know what's happening up until time 1, and then everything just gets shifted and repeated. So you know that part. And then from again, it's always playing this, like I like to call it Sudoku game. So you just need to match things which can be matched. In this Sudoku game, there's some trick which says these guys, they're not going to hit it, but actually it waits for the unit. That's some additional theorem from the first paper, it's more a general statement than this unit waits for time 1 whenever the weights here are 0 and 1. That's because of this ideal element story. But anyway, like explicitly we know that the filtration here at filtered piece 1/3, it's going to take H2, and eventually it's going to take H0 as well. For the second and third action, we had this S1 in the period 1/2. That's what's going to take one sphere, and the other one is going to take the other sphere. And then in the end, you get the unit coming from 2. So we get this explicitly as well. And which sphere is actually going to be taken? Well, that's going to be the non-fixed one. So if it was coming from here, this S1 actually takes exactly this guy. And that's a general feature. Like we didn't prove it, but that's a general expectation that these orbits are taking exactly the C-star fixed locus where it converges to using the C-star action. That's looking at these examples, this is exactly what's happening, but in general, it's hard to prove it. So like any orbits which appear in the columns, they're coming as some ZK isotropies, and that ZK isotropy has a C-star limit in some fixed locus. So the story is that these should take exactly these cohomological classes where they converge to using C-star action. That's the conjecture. However, yeah, hard to prove. Okay, so that was as far as the simple examples were considered. I guess I have like 2 more minutes or something. Yeah, so maybe just to finish up, and I just want to say that for these symplectic resolutions, we did some higher dimensional examples as well, called Stony varieties, which are quiver varieties. But also what was interesting is on the side, I did Higgs bundles moduli, and then in general, they satisfy all these criteria we need. So you get this filtration from the cis direction. And what was interesting there is was to compare it to the perverse filtration, also known as P equal to W, for people who do this Higgs bundles theory. And there, yeah, anyway, there was a nice representation theoretic picture of this filtration, that this filtration for the low dimensional Higgs moduli spaces, they recover these labels of imaginary roots for the fine linking diagrams. That was a nice result which I got with in some subsequent work. And then later on, in general, we realized that this Floer filtration recovers multiplicities of these components of the core. Again, for low dimensional Higgs moduli spaces. That was just like outside of symplectic topology world, this Floer filtration actually can have some sense in the algebraic geometry sense for this nice little family of low dimensional Higgs moduli. Okay, so I hope you followed all this. Thank you. Thanks so much. I hope that didn't go too fast, so I lost you.
Yeah, so what was the geometric meaning for these filtrations in symplectic? I think I lost it.
Right, so yeah, I guess from the, well, see, I guess the spectral sequence gives you one way to see. Like one was just the definition, like it's a kernel of this continuation map. And I guess from the spectral sequence perspective, it's, like something is in this, something is in the level lambda, if it can be represented with this, Hamiltonian periodic orbits of the period up to lambda. That's kind of, or it can be, right? This is the matching using these higher orbits. Right? That's the, because actually, that's like maybe symplectic explanation. So like you can.
And that's the information you can't directly read from the C-star action. Like it's
No. Again, this is a Floer theoretic information, but you go to the spectral sequence, and then so the E1 page of spectral sequence is basically just C-star action. So it's kind of, you look at the fixed locus, you look at the weighted composition, you look where they go, you intersect. There's some topology there, but as long as you can do that, you can get E1 page. And then if the E1 page is not ambiguous, like here, like it's not, everything's clear, then okay, this is filtered exactly by this guy. So it kind of gives you an interesting bijection between classes and certain orbits, certain Hamiltonian orbits of your well, or just orbits of S1 actually. Think about it. So when it works for higher dimensional cases, we've seen already that there's like, if this it's kind of Sudoku where but no, Sudoku should be only one solution, right? Whereas there's some ambiguity for higher dimensions. For higher dimensional examples, where you just kind of have two classes here, you don't know which class kills this one, and so on. That could happen, but that's as much as we can say for now. So, yeah, it's still there's still a lot of mystery behind it, like what else? How else we can compute it? This is kind of the state of the art for now.
One more question. I'm very biased on this topic, but since you kind of take everything with a C-star action, why not looking at equivariant homology, which probably would capture?
Oh yeah, we did it in the next paper.
Oh.
That's a good question, and that follows to Alex's talk. He's going to. So in the third paper, we did the equivariant. So the same setup, then equivariant Symplectic cohomology, using the action and using the loop rotation and using the interpolation, and realize it actually doesn't depend which one you do. And then we even like get to all detailed, like, so in the equivariant Symplectic cohomology story, there's a choice of which chain complex you want, which coefficients. There's this called like cyclic, something which means cyclic homology and localization and so on. So we do all those and say, okay, if it's Calabi-Yau, it's this, if it's Fama, it's this. So yeah, it's all there. So I guess Alex is going to go through that. And actually there you can also make sense of similar filtration, which kind of generalizes this because there's a U parameter there, like the equivariant parameter. And then when you put U to 0, then you get this filtration, but then you actually kind of get a bigraded filtration, which is interesting variant as well. So that can also lead, when you kind of specialize, you can lead to filtration QH. And then the next question is what's that, and so on. And yeah, and then we compute the equivalent Symplectic cohomology for these same projected like practice in the last paper. But yeah, all that I'll leave to Alex. he's also better in that anyways. So wait for it.